on this floor. Okay, so slab dead load on beam. So you go to floor load. So these are the load transferred from the slab to the beam. Always take notes. So total dead load here is 6 kN/meter square. So you say -6, it's acting downwards. And then come here. Remember I said that typically you would have to define the regions independently, and then where you have a one-way panel, you will have to tick one way, and then STAAD will calculate as a one-way and transfer to the beams on the longer direction. But for this purpose, we are assuming for a worst-case scenario that all the slab panels are two-way. Okay, that's great. So start slab life load on beams on the second floor. Go there, go to floor load, and then what's the life load on the second floor? -1.5. Great. Then you also have wall load as well too. So this wall load, you need to, on the second floors are also carrying wall load. So you put that there, and then you assign to the beams. Right? Good. So the next thing is on the first floor. We'll have something similar on the first floor too. So we would create two load cases, load case 10 and 11. Let me go through the STAAD editor. This is a brilliant environment where you can make changes to your structure analytic model. You can write your files on a notepad. As soon as you do that and close the editor file, it will automatically update the changes in STAAD. Those who know how to use STAAD editor model are advanced STAAD users like myself. Now I want to create load case 10 and 11, so I can simply copy load case 9. Since the loads are similar on the second and first floor based on our calculations, I would copy load case 8 and 9 to a new load case, call it 10 and 11. So we call this load 10, and then call the next one load 11, and change the heading to slab dead load on beams on first floor. Change this to first floor. And then slab imposed load on beam on first floor. Great. The last thing to change, since the floors are similar, is the coordinate of the Y range. When we're creating these floor loads, what is crucial is the coordinate point. As you go higher, the coordinate of the floors, the Y coordinate of the floors changes. So the Y coordinate of the floor here is 4.4. So you go back to editor and change the coordinates from 7.9 to 4.4. Great. As soon as you do this, just save and close. It will start to create those loads because they were written on the editor file. If there are errors in what I have just done, it will tell me there are errors, and I'll have to back check the syntax and check where the flaws originate from. So it is loading because I have modified the STAAD editor file. Good. So there are no errors. Let's check the two load cases I've just created. You could see load case 10 has appeared and then load case 11 on the first floor. Great, it has loaded it. Load case 11. So this is a very fast method of creating your load cases as well too, using the STAAD editor file. If you understand the syntax, the language of the editor file, you could just make some modifications there, save and close it, and then it updates the graphical user interface. Next thing for us to do is the wall load on the first floor. Just like on the preceding floors, you will assume that the entire beams on the first floor also are carrying walls. That's a conservative structural engineering approach, to assume that the entire beams are carrying walls as a worst case scenario. However, in a more precise engineering analysis, you would have to apply the wall loads exactly on the beams that are carrying these walls. It is very crucial. The next step is for us to calculate the wind loads. To apply the wind loads. So we say wind X and then wind in the Z direction. In the X direction, we had calculated the wind loads. Look at that. So X is the longitudinal direction, which is 90 degrees. In the transverse direction, it's treated as 0 degrees in the code of practice. So note that. So wind in the transverse direction is the wind load in the Z direction, and the transverse direction is catered for as 0 plus 0. Now, if you look at what we have done, just a very fast refresher, we talked about obtaining the basic wind speed. The code specifies that you need to get what the basic wind speed is from a meteorological data. The basic wind speed is the mean hourly wind speed at which the possibility of it being exceeded in a year is 0.05, which is about 1 in 20. Then that wind speed is converted to the gusts. Gusts are wind velocities that have a duration of less than 1 minute. They have a duration of less than 1 minute. and then the basic wind speed are sustained wind velocities. These are converted to gusts using certain constants or certain values. Those constants or factors are the attitudinal factor, the directional factor, the probability factor, and then the seasonal factors. These factors are obtained from the code of practice. So to cut things short, when we get the gust wind speed, you then calculate the wind pressure, which is half times rho v square, then times the external pressure coefficient times the size effect coefficient, and then you calculate the internal wind pressure, and then you calculate the effective wind, the total wind force. The total wind force is the wind pressure times the enclosure area. So for a closed area like you have in this building, where we assume that the windows are all closed, this structure will be rigid. The total force, the wind force, assuming that the pressure intensity between the two elevations do not change. Let's look at this. Now, the pressure intensity, you're looking at the transverse direction. So this is in the transverse direction. If the pressure intensity between 11.4 and 14.9 of the wind pressure doesn't change,